Hello students, how are you? Welcome to my channel again. Today it is the fifth lecture of de-Broglie's hypothesis, and I would like to conclude this topic in today's lecture. In the previous lecture we were discussing about some practical or numerical problems related with the de-Broglie hypothesis. So I would just continue that, just to tell you when to use this the relativistic expressions and when not to use relativistic expressions, because actually the calculations done during the relativistic calculations, the time taken is very large, and we can avoid that by using simple non-relativistic formulas. However, we must have the knowledge about the limits under which we can use these simple non-relativistic expressions to find the de-Broglie wavelength. Okay, I have made some examples just to avoid wastage of time. I would take the numerical calculations as done on by my hand on the paper. So I will use these calculations. If you want to verify, you can verify these calculations by yourself. Let us take an example of an electron which is accelerated by a potential difference of 11.24 into 10 raised to power 5 volt. Say, now this is an electron which is accelerated by a potential difference of 11.24 into 10 raised to power 5 volt. Now, if you are asked to find its wavelength, what is the wavelength of an electron which is accelerated by this much potential? Now, if you do not have the knowledge about the limitation of this expression, that lambda is equal to 12.27 angstrom divided by square root of voltage, then you may find wrong answer for the wavelength of the of the electron. For example, you will be just putting this value 1.12.27 angstrom divided by square root of 11.24 into 10 raised to power 5. Okay, you will get this answer. It will be 1.15 into 10 raised to power minus 2 angstrom, which we can simply write as 1.15 picometer. Now, as such, there does not seem to be any problem with the wavelength of the electron because it is going to be within this range. However, due to ignorance, we may write this answer for the wavelength. Actually, this answer of the wavelength of the electron is wrong. Why? Because this expression that we are using right now was obtained by assuming non-relativistic case. If I want to verify that whether this wavelength is correct or not, then we must know the circumstances or know the conditions under which this expression was derived. And we know that I have already done it in my previous lecture. You can refer to those lectures. That while deriving this expression, we used this equation half mv square. This actually is the problematic expression. It is non-relativistic expression for kinetic energy. It was equal to charge into potential difference, which gives us V is equal to square root of 2qV upon m. If I put the values, that is equal to 2q, because it is electron, I would use this expression value 1.6 10 raised to power minus 19. V is 11.24 into 10 raised to power 5 divided by mass is 9.1 into 10 raised to power minus 31. Now if I evaluate this answer, the answer will be simply V velocity of the electron, that will be simply equal to I have already calculated this answer in my rough work, and this will be 6.29 into 10 raised to power 8 meter per second. Now look at this answer. This answer is greater than C, because C is equal to 3 into 10 raised to power 8 meter per second. Obviously this is not acceptable to us, because no object can travel faster than speed of light. So this simply says that this method of finding the velocity is wrong, and since this method of velocity was used in deriving this expression of the wavelength of the electron, therefore calculating the wavelength of the electron at such a high potential difference is also wrong. Now what is the correct method? Now if you go by the golden line that I have told to you, that energy given during this voltage will be energy given to the electron will be equal to charge into potential difference. It will be charge, I would simply write E, and potential difference is 11.24 into 10 raised to power 5 volt. This will be, I can write it as 11 point, I can write it 1124 into 10 raised to power 3 volt, which is 1124 kilovolt, and this value is much greater than the standard value which I told in my previous lecture, that is 51.1 kilovolt. So obviously if we are aware of this fact that the applied potential is much more than the borderline potential that we derived by just multiplying rest mass energy with the 10%, just by took the 10% of the rest mass energy. So we will just be able to verify this, that at such a high energy the particle is subjected to a relativistic motion. So therefore we have just justified whatever precautions I have told you in my previous lectures to take while doing the numerical calculations. Okay, then what is the correct method and what is the correct value? Let us now do this. Now the correct value of kinetic energy, correct value is given by m minus m0 into c square. This expression actually comes from Einstein's special theory of relativity. You have to remember as such. Now we know that mass is given by m naught divided by square root of 1 minus v square by c square. This m naught is as such, and it will be c square. I can take m naught common. It will be 1 divided by square root of 1 minus v square by c square minus 1 and c square. And kinetic energy according to work energy theorem is nothing but charge into potential difference. Now if I put these values of charge then and potential, then I will be able to calculate the speed of the electron that it gains. The value of Q is 1.6 in 10 raised to power minus 19. Voltage is 11.24 into 10 raised to power 5, and it will be equal to m naught. Rather, instead of that, I would rather just use the value of Q is equal to E, and voltage is 11.24 into 10 raised to power 5, that is equal to, and it will be 1 upon square root of 1 minus v square by c square minus 1 and multiplied by m naught c square. I think I missed m naught here in the previous line. Let me correct that mistake. This m naught c square for electron is actually 511 kilo electron volt. This E will cancel with this E. I have done these calculations. With these calculations, you will get the value of V equal to 2.85 into 10 raised to power 8 meter per second. So you can verify this value yourself, and the answer will come out to be this. Obviously this is smaller than speed of light, and it is not actually much smaller, but it is smaller than the speed of light, and therefore you can see that this expression that I have used right now to find the velocity is correct. Now if this expression is correct, therefore the formula that we will be using, relativistic formula, will give us correct value of the wavelength. Lambda is equal to, that was equal to hc upon qv into square root of 1 plus 2 m naught c square by cube. If you put all the values that are given in this numerical, you will find that the value of the lambda will be 0.80 picometer. That is the correct value. And initially we were getting, this is the correct value, and wrong value that we obtained earlier was actually 1.15 picometer. This was the wrong value. Now I have justified by giving this example that it is very important to use relativistic expressions for high values of voltages. So I hope that you must have noticed, and you must have now appreciated the difference between the relativistic and non-relativistic expressions for finding the de-Broglie wavelength of the electron. Okay, that was something important I just wanted to share with you people, because many students they make this kind of mistake. It is not acceptable, such kind of mistake is not acceptable from an undergraduate student. He or she must have this knowledge under what circumstances what kind of expression has to be applied. So this was the numerical part. I would not discuss numerical part beyond this point. Let us discuss something else which is very interesting related with the de-Broglie hypothesis. Again, the topic, I would conclude this topic in this fifth lecture of the de-Broglie hypothesis, and my next lecture will be devoted to the wave mechanical treatment, or it will be the starting point, or the you can say it will be the foundation lecture for just studying Schrödinger picture or the Schrödinger equation. So next lecture will be devoted to that. Before that, let us now discuss an important feature of de-Broglie's hypothesis. We know that today in scientific world, the most modern model of the atom is the quantum model. However, before that, the model of the atom was Bohr's model. And in case of Bohr's model, there was a very important condition that the orbits are at fixed distance from the nucleus. An electron cannot revolve around the nucleus at any arbitrary value of the distance from the nucleus was not possible, or you can say the radii of the orbits could not be arbitrarily fixed. Only certain allowed values of radius of the orbit were observed, and that condition which permissible orbits are formed was given by Bohr as that the angular momentum, this symbol L is for angular momentum, is an integral multiple of h upon 2 pi. Now this condition is very easily proved by using the wave nature of the electron. According to particle nature of electron, nucleus in any atom is at the center and electron is revolving around it in circular orbit. Now this is the particle picture. However, if electron is showing the wave nature, then this kind of orbiter cannot be drawn. Actually, the wave nature of electron would assume that orbit is like this. And if orbit is like this, then then this orbit must contain a complete number of the wavelengths. Only then the orbit will be permissible. And if this is the case, we can see that the perimeter, average perimeter of this orbit, let us say this average value is 2 pi r, where r is the average distance of the orbit from the center of the nucleus. So the wave nature of the electron just allows us to understand that there must be even number of wavelengths involved in the orbit of the electron around the nucleus. Therefore this 2 pi r, sorry, I used the word even number, actually it is the complete number of wavelengths, and the wavelengths cannot be incomplete, means such kind. Let me take the example. You cannot have an orbit like this. This kind of orbit is not possible because the wavelengths are not completing. So therefore we must have 2 pi r is equal to n lambda. If 2 pi r is equal to n lambda, then I can use 2 pi r is equal to n. Lambda is nothing but h upon mv, where lambda is equal to h upon mv comes from de-Broglie's formula. And I can take mv on the left hand side and 2 pi on the right hand side. It will become mvr is equal to nh upon 2 pi. mvr is nothing but the magnitude of the angular momentum of the electron revolving around the nucleus. So therefore L will be equal to nh upon 2 pi. Now this is a condition which was actually the second postulate of Bohr's atomic model, and this condition we have proved now by using the de-Broglie concept. And it's interesting that this postulate, which was appearing to be very ad hoc in nature, it is being proved by using the de-Broglie concept. But it does not mean that Bohr model completely takes into account the wave nature of the electron. Actually, quantum model of the atom takes into account the wave nature of the electron completely. Why? Because in Bohr model there were certain limitations due to which it was replaced by the quantum model. For example, the concept of orbitals was not there, and probability densities. We know that the shape of the orbitals, s orbital is spherically symmetric. P orbitals are dumbbell in shape, px, py, pz, etc. So I will not go into those details because it is a different topic altogether in itself. So I will not touch that. So this was something important I wanted to share with you. Next, the last topic related with the de-Broglie hypothesis for today's lecture, and is the experimental verification. Experimental verification of the wave nature of matter, and that was by, I have just recalled that experiment many times during my previous lectures, and just now I am giving you the details of that experimental demonstration. And this experiment is nothing but it is the famous Davisson and Germer experiment. Davisson and Germer experiment. Now, Davisson and Germer experiment. Let me give you just its experimental details. So this was a crystal in their setup. This was a crystal. Of nickel. And there was a cathode gun. which was emitting electrons due to thermionic emission by this very low EMF potential difference battery. This electron beam was then passed through a narrow slit which is called as collimator. This narrow slit is called collimator. So collimator actually converts this electron beam into a fine beam, and this collimator is kept at negative potential with respect to this battery. So it means there is an accelerating potential V connected between collimator and this nickel crystal. So this accelerated electron beam strikes normally. On the surface of the nickel crystal, and after striking it, it was scattered in various directions. Okay, the intensity of the electron beam scattered in various directions was not same, and since it is an electron beam, so intensity of the electron beam will simply be represented by the electron current if I am able to detect it. So if we have a detector, let us say here, it is just the outline of the detector, kindly remember. So let us say this is an electron beam detector here. So it will note some current I1 and angle of scattering phi1. So if actually this detector is mounted on a rotating disc, so it can rotate along the arc of a circle. So if I just bring this detector at this place, just by rotating the disc, mounting disc, then what we can do, we can measure new angle of scattering phi2 and new current I2. The current here was I1 and angle of scattering was phi1, and current here is phi2 and angle of scattering is I2. During whole of this process, when we were measuring different angles of scattering and corresponding current, the voltage V is kept constant. So therefore we can make an observation graph that if this is the incident beam, then I can make some scale, I can choose some scale. Let us say that scale is it is just for the demonstration purpose only. Let us say I choose some scale. Let us say 1 centimeter is equal to, let us say 10, current will be very small, let us say it is picoampere. So if let us say this current I1 is 10 picoampere and let us say I2 is 30 picoampere, then this will be represented by an arrow of or a line of length 1 centimeter, and this current will be represented at a length of 3 centimeter. This will be, its dot will be at a length of 1 centimeter from the point of scattering. This is the point of scattering, and its length will be 3 centimeter from the point of scattering. With respect to incident beam, the angles will also be different. Means, let us say this angle is maybe let us say it is 50 degree. So if I draw a line at 50 degree, let us say 50 degree, then this line will be 3 centimeter long. So I will get 1 point. Similarly, let us say this angle phi 1 is, since it is a wider angle, let us say this is 80 degree. So if I draw an angle of 80 degree with respect to incident beam, and I will draw a line only 1 centimeter, and I will just get 1 point. So in that way I can just plot many data points on the graph paper, and when I join these data points, let us say there are various data points like this, then I can join these data points to observe the graph. Then I can obviously I will just keep this reference line in the graph, and all other these arrows can be erased. So this is the method that was adopted for plotting the graph. This is incident beam, and this is not one scattered beam. This is actually the collection of many scattered beams. And if there is any arbitrary point on the this curve, let us say this is any arbitrary point on the curve A. On the curve, let us say there is any arbitrary point A. I want to find what is the intensity and what is the angle of scattering. I would just simply join point A with this scattering point O. Then I will measure this length, and this is the scale. Whatever is the length, I will multiply with that scale, and that will give me the current. And I will measure this angle between this line and this line, that will give me the angle of scattering. Now let me discuss some theoretical aspects related with this. First of all, this is the surface. The beam is normal to the surface. However, it is not necessary that the incident beam is reflected by this surface. Actually, this is a nickel crystal. It contains lattice planes, and the lattice planes in the nickel crystal may have many alignments. If you study the concept of diffraction of X-rays from a crystal, you would come to know about this point, that in a given crystal there are many possible orientations of a single crystal for different lattice planes. So a single crystal may show up different sets of lattice planes which can set up the diffraction, and that diffraction pattern will go in the three-dimensional space around the crystal. And due to this reason, in fact, a crystal is called three-dimensional diffraction grating, and that diffraction will be according to a famous law which is called Bragg's law. And Bragg's law says that the diffraction of nth order from a crystal will follow this expression. Actually, this was Bragg's law of diffraction of X-rays from a crystal. Here we are getting diffraction of electron beam from a crystal. The only difference is that we are using here electron beam instead of the X-rays. Now, what you would remember, we must remember here that D is actually the lattice spacing which is responsible for Bragg's diffraction at a given angle of scattering, and theta is not the angle of scattering. Theta is actually angle of glance. It is the angle with the lattice plane, not the surface of the crystal. It is the angle with the lattice plane and the incident beam. That is angle of glance. Okay, let me first check what would be the result of Davisson and Germer experiment. What was the result or what was the observation made by Davisson and Germer experiment? Okay, they plotted this kind of graph for various values of V. I can put an arrow over here which tells me that this voltage is adjustable. For a single set of graph, this value should be kept constant and only I would be changing phi and measuring corresponding value of I. So the first graph was plotted when accelerating voltage was 44 volt and the graph was very diffused. Then same graph, similar kind of graph was plotted when the accelerating voltage was kept as 48 volt and the graph showed some sharpness, and the graph was plotted by keeping the accelerating voltage 54 volt, then the graph showed very sharp peak, and the point which was at a maximum distance from the point of scattering was this point A. If I join this point A from O by a dotted line, that will give me the average angle of scattering for this point A. This angle phi was measured experimentally and it was observed that phi was equal to 50 degrees and graph showed first peak. This graph did not show any peak, this graph did not show any peak, this graph showed peak. It means when accelerating voltage is 50 volt, most of the scattered electron were scattered at an angle of 50 degree with respect to incident beam. What happened when we increased this voltage further and the graph again became diffused. It was at V is equal to 58 volt, and when we just increased the voltage, I can erase this portion now. When we increased the voltage to 64 volt, the graph became further diffused. It means initially diffused graph just moved toward sharper, then again sharper graph moved toward diffused graph, and therefore the first peak was observed at angle of scattering 50 degree when accelerating voltage was 54 volt. Now, if that observation is kept in mind, then we can have some theoretical portion. So I can erase this region now. Now, suppose in this crystal which I have shown, suppose this is the crystal. Now I will show it by unshaded region. Let us say the lattice planes are inclined in this fashion, which are responsible for diffraction. And I would just, this is not lattice plane, it is just for the sake of simplicity. The lattice planes are inside. I have just extrapolated. Now suppose this incident beam comes and strikes here, and it is going in this direction. This angle, this is incident beam, this angle is actually phi, which is equal to 50 degree. And this is the lattice plane responsible for Bragg's reflection. This is Bragg's plane actually. Any plane which is responsible for Bragg's reflection is called Bragg's plane, and this angle will be angle of glance, theta. So since the beam has suffered Bragg reflection, according to law of reflection, if this angle is theta, then this angle will also be theta. Now it is clear from this diagram that theta plus phi plus theta must be equal to 180 degree, and therefore 2 theta is equal to 180 minus phi. Since phi is 50 degree, so it will be 180 minus 50, that is equal to 130 degree. Therefore theta is equal to 65 degree. Now it means if I use Bragg's law, then according to it, since this is the first peak that we have observed in all these 5 graphs, therefore I can use n is equal to 1. It was the peak at 54 volt and phi is equal to 50 degree was first order diffraction peak, so I can use n is equal to 1. And d, the lattice spacing, we have to remember it, was actually 0.91 angstrom. So if I put this value of d, this value of n, and theta is equal to 65 degree, and I just calculate, then this value will become 2 into 0.91 angstrom into sine of 65 degree is equal to 1 into lambda. This will give me lambda is equal to 1.65 angstrom. So this is well established Bragg's law. Kindly remember, Bragg's law is for diffraction of any wave from a crystal. It requires only one condition, that the diffraction must be from a crystal and the wave should have wavelength comparable with the lattice spacing of that crystal. Only then the diffraction will be observed. And if the electron beam is actually diffracted, it has diffracted, then the wavelength must be equal to 1.65 angstrom according to Bragg's law, which is a proved or well established law. Now what is the new law that we have just discussed in the previous lectures? The new formula for wavelength of the electrons is actually 12.27 divided by square root of voltage. I can use this formula right now because the accelerating voltage is just 54 volt. It is actually in angstrom. So if I put the value V is equal to 54 volt, then I will get this answer to be 1.67 angstrom. Now this expression of lambda, this value of lambda, which is 1.67 angstrom, it came from de-Broglie formula, and this value of lambda, it came from Bragg's law. This is a well established law, we already knew about it, and this is the new formula which was to be verified. And these two results are actually within the experimental limits in agreement with each other. Therefore, the agreement between these two values, 1.65 angstrom and 1.67 angstrom, it is a confirmation of the fact that the electron beam has diffracted from this crystal, just like if an X-ray beam would have been made incident on the same crystal by using the Bragg's law. So this just experimental observation proves that electron beam has shown diffraction. Since diffraction is the property of the waves, it means electrons are showing the wave nature. So since every matter contains electrons, so therefore if electrons are showing wave nature, therefore matter also possesses wave nature. So this experiment, this famous experiment, was actually a confirmation. It was a confirmation of the de-Broglie's hypothesis. Traditionally, it is called de-Broglie's hypothesis. Till date, it is called de-Broglie hypothesis, since it has been proved now. In fact, we can say that it is now a de-Broglie's law. So I hope you must have enjoyed all these lectures related with the de-Broglie's hypothesis. I would end up the topic today with this lecture, and in the next lecture we will be discussing about this Schrödinger equation. I will not straightforward jump into Schrödinger equation in the next lecture. I will just give some basic requirements for taking understanding what the Schrödinger equation actually means and how we should deal with it. So till then I would just expect that you must have enjoyed today's lecture, and goodbye, and we will meet again in the next lecture related with the basics of the Schrödinger equation. Thank you. Thanks a lot.